Hi everyone. Very happy to be speaking here. Very excited to be speaking to this audience interested in token engineering specifically, because I remember when this initiative started not so long ago, when it was kind of first ideas around it, I think by Trent and others. It was super exciting back then, but it's great to see that there are like token engineering meetups all over the world, and more companies and people get involved in this. So yeah, very exciting. Okay, so my name is Piotr, and I'm the founder of Incentivai. And Incentivai simulates smart contract economies. But because we have quite a bit of time today, I've split this session into 4 parts, and we will be able to go into a lot of detail of incentive structures themselves, but also how Incentivai works and so on. So so in the first part, I will introduce the whole concept of kind of incentive structures, what we mean by them, what we mean by designing incentive structures and optimizing them and so on. And only then I will go into how Incentivai actually works, what it actually does, how you can use it. And then we will end with 2 case studies that will add a lot more kind of context into how you can actually use it. Okay, so let's start with the first part, the introduction to incentive structures. So I like to start with this definition of blockchain that I came up with myself, which is that it's self-enforceable execution that nobody owns. So what I mean by self-enforceable here is that it's self-enforceable in an economic sense. If I create a smart contract on the Ethereum blockchain and I deploy it today, then I can be pretty sure that it will still be up and running tomorrow or a week from now. And what is this trust kind of based on? It's probably not traced on any like particular miner on the Ethereum blockchain or anything specific about the code or the technology. But I would say it's because the incentive structure that runs Ethereum is such that there are actors who are financially motivated to keep it running. And that's what I mean by economically self-enforceable, is that there are people who essentially would lose money or could win money by keeping it going and making it behave as we want it. And then the second part, that nobody owns it, that's kind of the idea of decentralization that we know. And the reason why I like this definition is that, to me, it highlights the 2 conditions that need to be met for a particular use case to require blockchain. So I would say that a particular use case requires blockchain and not any other technology we've known before if it needs to be self-enforceable in this economic sense and decentralized. So let's dig a bit deeper into those 2 concepts. So the nobody owns it part, that's something we're very familiar with. That's the idea of decentralization, and it basically means that there is no one entity that has the power to change the rules of the game, right? Decentralization obviously is not binary. A project can be decentralized to some extent, but again, it's this idea that the power to change the rules of the game is not concentrated in a few hands. And kind of by definition, decentralized systems would be very inefficient. So the reason why is that, well, there would always be some element of kind of referendum. You would always have a number of actors that need to contribute to a particular decision or to reaching consensus. You can use different technical solutions to try and make it more efficient, but like it's just by definition, it's always going to be relatively inefficient. That's why many of such decentralized systems will end up being not economically self-enforceable, just because it would be expensive. Whenever there is a system where full decentralization is not necessarily needed, then probably the more economically viable solution would be to use something more centralized. Now this takes us to this concept of being economically self-enforceable. Obviously, a project doesn't need to be decentralized to be economically enforceable in that sense. I would argue that you can say the same thing about Google, right? So we trust that Google will still be up and running tomorrow, not necessarily because there are no bugs in their code or that there is enough redundancy in their servers, but specifically because there is this incentive structure around it, that there are so many people who are financially motivated to keep it running. And now this whole consideration of systems being economically self-enforceable and decentralized, this kind of underlines once again the kind of genius behind Bitcoin, because Bitcoin was this first invention which managed to become, well, relatively very decentralized and at the same time economically self-enforceable. Is that we have all these people still today working on improving the system, and the system itself seems to be funding them to do that work. So that is pretty amazing, and it kind of reminds me of this quote by Ralph Merkle, who was essentially I think the first person to suggest that Bitcoin is this new form of life, right? So that's a very interesting way to put it. But there is definitely something to be said there. Bitcoin has this Bitcoin, but also other blockchain projects have this fascinating capacity of adapting itself to changing circumstances during their lifetime, right? So you have things like block difficulty in let's say Ethereum blockchain, which adapts itself to changing circumstances. But even more than that, Bitcoin somehow magically managed to quote hire a number of people who are being paid for working on the protocol, who are being paid for spreading the word and constantly doing research on how to improve it. So that's really fascinating that we have this new kind of life form that manages to adapt itself during its lifetime, but also to kind of hire other actors and motivate other actors to help it sustain itself. So this slide kind of summarizes that. And what's also interesting about Bitcoin and other blockchains and other blockchain projects is that if we look at the blockchain ecosystem as a whole in general, then we can see that now these different protocols, they seem to compete against one another, or they compete for limited resources like the attention of people or the different use cases that are possible in the system. And in what way do they compete? Well, I would argue that those systems are all defined by their different incentive structures. Like when you deploy your cryptoeconomic system, what defines it's its incentive structure. And that's what's going to determine whether it succeeds or not. So, so that kind of defines in the long run which project will be successful and which not. The ones that have an incentive structure that works better given the current circumstances in the ecosystem. And so this is the way I like to think about incentive structures, to kind of split it in those two parts. So when you're a designer of an incentive structure, the first thing you do is to think about what elements will make up your system and how you would actually design it. And those things are entirely in your control. This is before you launched it, and you can make all the decisions that you want. So in case of cryptoeconomic systems, this could be things like the shape of your bonding curve, or your slashing conditions, or maybe the bonuses of your long-term stakers. So this is all the aspects and hyperparameters that define how your system works. And I use the word hyperparameters for them because it's a parallel to how machine learning models work. So if you want to create a machine learning model, then first you define sort of its architecture, so its hyperparameters. So that's going to be like the number of layers of your neural network, or types of neurons or connections between them. And the thing about hyperparameters is that they're all in your control. Hopefully you can use all the time in the world to choose them right, such that they work once they are deployed. But then once the design of your system is decided, it's locked down, and once it's deployed into the world, you can't really change it. I mean, in theory, you can do things like releasing an updated version of your software, but that would rely on users switching to that. But in theory, what you want to do is to design a system that's going to work kind of from scratch, from version 1. And once you deploy your system, what happens to it can be described by its parameters. Things like token price or distribution of users' activity, so what it is that users actually do, or maybe different bribing attacks that users undertake. And these parameters, this behavior of a system, this is completely out of your control. So going back to this example of a machine learning model, this is going to be the time when your machine learning model actually gets trained, right? So once you've defined your hyperparameters and what your network looks like, the actual training is completely out of your control. What actual weights and what actual parameters will be learned. Those are completely defined by the world that your model works in and by its training data. Yeah, so to sum up, this split of incentive structures into these two parts is a useful way to think about it. So first, you design your system. You make the decision about your hyperparameters. Then once your design is ready, you are ready to deploy your system. And when you do that, then what happens to it, which is the evolution of the parameters, those things are out of your control. And what happens to the system is entirely determined by its design and by the external circumstances, so by what is going on in the outside world. So this consideration brings us to an interesting kind of realization that as system designers, what we would love to have is to have some system, some solution, we're going to call it a black box here, that takes as an input our system design or the hyperparameters that describe our system and gives us as an output the resultant behavior that we're going to see in terms of these parameters like the evolution of the token price. So ideally what we would have is we would say, okay, this is my design in terms of hyperparameters. I'm going to feed it into this black box something, and this black box something is going to predict or approximate the future for me and tell me what the likely resultant behavior is going to be. One thing to remember here is that our system is always going to be deployed into the real world and is going to interact with real people. So we need to also feed it some assumptions about the actors in the system. So usually it's going to be something like what we assume about the motivations of the users, maybe something about whether the users are irrational or not, what drives their behavior. But the kind of holy grail of the design would be if we could have some black box that takes in our assumptions about what users care about and our system hyperparameters and tells us what our resultant behavior would be. And now the question is, what this black box could possibly be? Because if we had it, then our design could be thought of as this kind of scientific method of iteration. We could say, okay, this is my initial design, these are my initial assumptions. Let's see what happens. If I'm not happy with the current behavior, then I can change something in my design, check how it works across a different set of assumptions, and kind of that way converge towards a design I'm happy with. Okay, so what could this black box be? So probably the most kind of ambitious approach and the most kind of pure approach is to just use game theoretic analysis. So to just say, this is kind of like a math problem or a mechanism design problem where I know my system design, I know my assumptions, so let me kind of find a closed form, almost closed form solution to what the resultant behavior would be. So what we would do then is to try to like work out this math problem to find like dominant strategies for users or natural equilibrium for users. So I would love for those solutions to work. They would be extremely insightful. But the problem is that they're probably not applicable to complex systems. So we know from kind of mechanism design literature that it has some solutions for simple systems like auctions, and those have been developed like decades ago. But anything more complex than auctions very quickly becomes intractable. So what you need to do is you need to make some simplifying assumptions, right? So you need to take your complex design and express it in such a way that it's much simpler, and you can actually analyze it in such a way. But then the risk is that while doing that, you will be kind of forced to miss out on some very important aspects of your system that would make your results, well, far from what you'd see in reality. And also, as we've said before, we would love to be able to incorporate some assumptions about human behavior, right? So some deviations from rationality, some agents being risk averse to some extent, maybe short-term profit maximizers. And again, every new assumptions, every new mechanism that we introduce can very quickly make those problems completely intractable. And on top of that, such an approach is extremely time-consuming, because every time you want to add something new to your system or add a new set of assumptions, you need to almost start this from scratch, because this is kind of like a theoretical analysis, and you always need to make sure that nothing kind of fundamental hasn't changed since the last time you did the math. Okay, so let's see if there's anything else. So maybe we can kind of just have a go, just try it out. So do something like a testnet release, or maybe a small-scale experiment with some real people. So that, again, it could be very insightful, because now it feels like we're closer to what the real thing would be, because we have some real people involved. But I would argue that here the problem is that we're not really doing any stress testing. So what we're doing is we have a world which is much less kind of extreme than the real world would be. And I would argue that when those cryptoeconomic systems just crash catastrophically, it's going to usually be in those extreme cases when there's lots of users, lots of money involved, and people are really motivated to find ways to game the system, but even if not being malicious, to act in their self-interest and find out those optimal strategies. So here, participants on the testnet or on an exercise that mimics the real network wouldn't be as motivated to really find those optimal solutions. And the real risk is that we could kind of grow complacent and become too optimistic about our design, or even worse, start optimizing for this kind of naive approaches that users aren't as kind of conscientious in finding their optimal strategies. So another possible solution would be to use what I call random simulations. And what I mean by that is that you could kind of build some model of what your system looks like in like any programming language or even in Excel, and then maybe like identify different things users can do, and then use your intuition to say, okay, what percentage of the time they would do particular things. And while this could potentially identify some failure modes, like this is still entirely based on your intuition, and you're kind of hard coding users' behavior into your analysis, which means that you're unlikely to find anything kind of surprising and new, and you're also unlikely to find any behavior that really emerges out of your mechanism, because you're kind of hard coding all actions into users' behaviors. So finally, this kind of leaves us with the Incentivai approach, which is simulations with AI agents. So the difference here is that we would take, as you remember, those assumptions about what motivates users, and we would put use those as objective functions for machine learning agents that figure out their strategies for themselves. And now we can also incorporate some non-rational behavior into what the agents do, for example, in how they use their objective function to find their optimal strategy. And that way, the hope is that the agents can behave more like real people, but also potentially behave more like smart, malicious actors who just try out different strategies and find the most optimal way to attack the system. So, so that's the end of part one, and we're going to talk about exactly what I mean by all that in future parts. But if there are any questions right now, I'm happy to answer. Yeah, there's one, and I think we need to... Yeah. Okay, thanks.
Cheers. So thank you very much for the presentation, very interesting. My question here is, you mentioned the fact that there's a problem associated with using random simulations. My question here is, when you come up with those AI agents models, how do you prevent that from happening? Because in the first place, you still somehow infuse, like the model that you use for your AI algorithm is also subject to, you know, randomness in a sense that you pick the one you like, you pick up those agents yourselves.
Okay.
You know what I mean?
Yeah, I think so. So obviously, I will be talking much more about this in future parts. But what I can say is that, yeah, I do put a lot of effort in trying to remove all of my intuitions from what the agents do. So all the information that I encode into the agent is to say, this is the objective that you want to optimize for. So, for example, you want to make as much money as possible, right? That's a simple, greedy agent. And then the agent, all it does is it can observe the environment, it can observe the different actions it can take, and it can kind of, based on each action, approximate what the likely outcome would be in the long run for it. So I don't incorporate any kind of prior biases into the agent, but rather it can figure out what it's best, what is best for it in the long run. Obviously, like it's true that I do pick like what machine learning model sits inside agent's brain, but that's the sort of bias that you always get when you do machine learning.
Okay, so somehow I'll give you the mic in a second. So somehow you're saying that you're picking up goals, and then you let the machine decide what strategy to opt for based upon these goals, but you don't get to decide a strategy that they choose. Okay, fair enough.
Great, thanks. To connect to your question, so if I could summarize your answer, I would summarize it as giving the agent simple goals, but allow them to have arbitrarily complex observations. Is that kind of how you could summarize the approach that you just mentioned?
I'm not sure what you mean by arbitrarily complex observations.
I mean, depending on what there is to observe, they just get to observe and evaluate what kind of effect. Okay, let's forget that.
But
I have a different question actually,
okay.
but I think we can talk about this later. About testnets, you mentioned that testnets may lead to certain suboptimal results. Is that the same for incentivized testnets? Because if you set the incentives right when you launch a testnet, you could essentially model the same behaviors that you are trying to safeguard against before launching the mainnet. And I would wonder what your opinion is.
Yeah, very good question. So when I said about optimizing or like finding suboptimal incentives, probably what I had in mind was these like small scale experiments when you set up like a game with real people, real money, and they like try to game the system. But I think it also applies to testnets. So I would argue that if you set up an incentive structure on a testnet and there's no real money, or there's a lot of money involved, then what you could do is you could, for example, reach certain conclusions that, for instance, a certain hyperparameter setup is perfectly fine, just because no user was incentivized enough to explore a certain adverse path, really, and you could kind of go in that direction of optimization of the system and make it vulnerable for those things, just because it never occurred to a user to be malicious enough, or they were never motivated.
So, employing the strategy of trying an incentivized testnet could be used in conjunction with simulations. Is that what you're saying? Because that would probably, because the way I understood your reply right now was that if you only or rely heavily on an incentivized testnet, if your incentives aren't high enough, which is obviously requires a lot of capital expenditure, would mean that there are certain risks that are never even getting looked at because the incentive is not high enough. And you could combine these approaches to kind of make sure that you cover more ground.
Yeah, that makes sense. Like, all I'm saying is that, like, systems break in extreme circumstances, right? And you're unlikely to get extreme circumstances on a testnet, right? So that's where those are the things that testnet won't give you and a simulation will give you, right?
But my question is, I mean, the power of AI is also limited. I mean, they cannot really foresee all options of behavior which a human could. Yep. For example, if you stay with a Bitcoin example, how could you foresee, for example, that people concentrate mining power and all move to China, and they're highly concentrating miners in China, which are a real danger to the system, right? I mean, I wonder if someone programmed the test, AI test 10 years ago with our knowledge, if he came to the result, this is going to happen. Because it's a quite complex process that the increasing power, energy expenses incentivize people to move to countries where the power electricity costs are lower and concentrate mining power and all this. I mean, how can AI has to be very...
So this is a really good question. So the current state of AI, we obviously know where it is. So there are some tasks which are absolutely impossible. So like an AI today is never going to kind of hold this microphone as well as I do, but it will beat any human being at Go very easily, right? So there are some tasks that are extremely easy for machine learning. And so one interesting observation here is that actually blockchain problems are, or like blockchain simulation problems are relatively kind of easy to understand for machine learning agents, because kind of on a blockchain, everything is a number, everything is well structured, and those economies are relatively closed. So it's not like an AI system needs to figure out that, you know, you can leave the building and go to a shop and do something, right? So those problems are kind of well tuned for machine learning systems. But going to your question, yeah, it's very much the question of like where you draw the boundary of the environment, right? If the machine learning system has no idea that China even exists, then obviously it's never gonna figure it out. But if you do encode into your system some idea of, you know, various constituencies, various countries, different economies where certain costs are higher and lower, then I really don't see why an AI system wouldn't figure something like that out. But okay,
just the fact that the energy prices change over time is a problem that neither a human being nor AI can foresee. And that's why actually things happen and you cannot predict them. Yeah, for sure. So there will always be limits to it. But what I do like about simulations is that, like, all you need to do is, for example, realize that energy prices are a factor in this, right? And then you can add this factor and run and like regress all your simulations across that factor very easily, right? And then see, yeah, if you don't realize that something is a factor at all, then that's going to be a problem. But yeah. But that leads to a similar system than the whole testing before, because it's a question of the setup, what the results or the outcome is, right? As many parameters as you oversee in the setup, as more the result will not be valid.
Yeah, that's very true. But I still think that there's a lot to be learned, even if we missed some small detail.
I agree. Yes.
Yeah, so.
Thanks.
Could you tell us a little bit about data that you feed to your models and where you get it?
So I'll be talking more about models later, but thing about data that I probably don't mention here is that most of these projects won't have any historical data, right? And that's a very important thing. Like when you're launching something on a blockchain, you're very likely the first project ever to be doing this sort of stuff in this particular economy, in this particular setup. That's why I really wanted this system to potentially not require any historical data as such. That's why the system is set up as a, you can think of it as a game. Like it was kind of inspired by like the AlphaGo setup. So you can set up your environment as a game, and the training data is generated automatically. So even if there's no historical data, you can still like, run your simulations.
I just want to add to his question, just how will the AI actually socialize, you know, because what I understand with the blockchain and the cryptocurrency is like the value is only generated when you trade it. Like more you trade it, the more the value will increase. And how will it actually trade? You know, how will the AI agent trade with the other AI agent? Because they don't eat food and they don't live actually, right? So they don't have the value of money like human beings. That's the only, like, how will they measure the value of money? Because they don't consider it as a value. We consider it.
Okay, so yeah, that's an interesting one. You know, so a machine learning agent observes the world and it has a reward that was encoded in it, and it can look at the world and it can like assess how good this particular situation is, right? And I think that's all an agent needs to like recognize the value of money, right? Even if, because it might be that its objective function is to earn as much money as possible, but even if its objective function is something like, you know, don't die out of hunger, and you actually have this idea that an agent needs to, you know, make some money and earn some and buy some food to survive. Like it's gonna figure out how it should value food in that sense.
So almost we need to model the whole world, kind of like.
I mean, I don't think that's necessary to like get your incentive structure of your system right, but
okay. Yeah,
but yeah,
almost, yeah.
So when you're looking at the final outcome, you know, the final state of the game, are you also, are you evaluating that first by hand, or do you have some predefined outcomes? You know, what is the final equilibrium that either individual agents get to and that will stop your sim, or once, yeah, like is there equilibrium? Have you gotten to that point, or is it a manual process where you stop after so many generations?
Right. So. Yeah, so I'm not sure about the concept of equilibrium, but one important point here is that it's not quite an answer to your question, but maybe it does in a way. So if someone comes to me and says, this is how our system works, and we explain it to be, we expect it to behave in such and such and such a way, and we can trust your simulation if it shows this result, right? Then the thing is, as you remember, like one of the inputs to the simulation is assumptions about actor motivations, right? And that's one of the inputs. So that means that a simulation can, in theory, like show kind of any result that you want, right? So right, because I can always tune the parameters such that it show whatever I want, right? So there will never be a case of kind of validating that that's for sure kind of correct, right? The only way to validate it is to kind of run the simulation several times, optimize the system that way, and then have the system running for a long enough time, and be kind of, and then realize that, well, the design that we chose actually ended up working. So yeah, so in that sense, we need to be careful, because we need to think of these simulations more as like a developer tool rather than something that gives us answers, because there are no clear answers. There are only kind of trends, and there are only kind of there's only this black box that takes some inputs and shows you some outputs. But there's no definite answer. It doesn't predict the future in that sense. Mm-hmm.
Piotr, taking a look at Blackbox, so you say my inputs are potential objectives of the agents, and the output which I can provide are the behaviors, right? Mm-hmm. Which is, in a sense, very intelligent, because my guess is, maybe you can confirm or tell about your experience, that the number of different objectives in this world of human beings is potentially much smaller than potential behaviors, which we are not able to foresee. So I don't know about recent projects. Would you say that, let's say, 2 years from now, we have a set of agents, different objectives of agents, of course, represented in different objective functions, but general objectives in a blockchain systems are less than 20, probably?
Yeah, that's a really good question. So where I see this kind of approach evolving to, and probably if we, like towards the end of the presentation, we'll have more context, but where I see this approach going is that, yeah, we will have like a standard maybe library of different like assumptions about objectives, and also a standard library of different like deviations from rational behavior that we're aware of from like psychology or behavioral economics, or, you know, thinking fast and slow and things like that. So and then we will be able to like literally run like a preset set of tests for any cryptoeconomic system. So we would be able to say, for any cryptoeconomic systems to even be considered, it needs to run through this like 2 million different tests, and we need to make sure that it behaves reasonably in kind of most of them, because we have this predefined library of different objectives or types of non-rational behavior, for example. And this library would probably keep on growing over time. But yeah, there's definitely a room for some sort of a standard way of approaching that. Yeah.